This PowerPoint talks about centripetal motion.
So centripetal motion has a lot of measurements that we need to kind of look at and see what the relationships are between those. So first off, it talked about an object that's moving in a circle. It's got a circular path. Now it can get more complex than that. We can talk about objects moving at an ellipse, but for the sake of this unit, we're going to just talk about the circle. So what is the direction of the radius? Now that might be a little bit weird to think about, that radius has a direction. But if you were to think about radius and what direction it would be, hopefully if I say that the radius is from the center outward, that would make sense. It goes out from the center. Now, what about the velocity? What direction is the velocity? Okay, so if you were to hold something and move around in a circle, as you're going around, basically what happens is if you let go of it, it looks like it moves away from you. But in fact, it doesn't really move away from you. The reason it moves away is because it actually goes tangent to the circle. It actually goes this direction. Now, if you're the one in the center turning, as you're turning, it looks like it moves away just because it's moving tangential. So we call that a tangential direction. So regardless of where you are, where you let go of this object, it'll always be tangent to the circle, tangential velocity. Now, what about the acceleration? What direction is the acceleration? Now, the acceleration is actually towards the center of the circle. And the reason we know it's towards the center of the circle is because this velocity moving up this direction, in order to start turning to the left, that means the acceleration has to be to the left. So the acceleration and the velocity are always perpendicular to each other in a circle with circular motion. So the acceleration is towards the center of the circle, and the term we use is centripetal, which actually means a center-seeking acceleration. The term centripetal means a center-seeking acceleration. So the equation that we have for this center-seeking acceleration is going to be equal to the speed squared divided by the radius. So whatever that speed is. So notice that I'm not saying the word velocity, even though we kind of use the same letter for it. Velocity actually implies a direction as well, and the direction is always changing as it goes around. So it's going to be the speed squared divided by the radius to find the centripetal acceleration. So in this example, you see that as the object moves around, the acceleration is towards the center of the circle, but when I release the little thing there, you can see that it moves off in a direction that is tangent to the circle. So the acceleration is always, the disk was always pushing it towards the center of the circle, and as it was being pushed towards the center of the circle, it stayed in a circle, and when I released it, when I lift that hoop upward, it went off at tangent to the circle.
All right, so let's talk about 2 points in the path because we're going to develop an equation out of this. Let's suppose we got this point right here where the radius is radius 1, velocity 1, and then it moves to position 2. Just a little bit of time later. It takes a little bit of time in order to get from point 1 to point 2 as it's moving around in a circle. So we're just kind of taking a snapshot as this thing's moving around as it goes from here to here. Now, realize that the magnitude of the velocity or the speed doesn't change. It's going to move at a constant speed, but the velocity actually is changing because if you remember, velocity is a magnitude and a direction. Even though the magnitude's not changing, the direction is, therefore the velocity is technically changing. And if the velocity is changing, that means there has to be an acceleration. And we know that acceleration is toward the center of the circle because that's what the centripetal acceleration is. Now, let's look at these two points, the vectors that are at these 2 points. So the radius vector at point 1 and the radius vector at point 2, I want to look at that and make a triangle out of it. And basically, change in radius. The change in radius is radius 1 minus radius 2, which is radius 2 minus radius 1, which is radius 2 plus a negative radius 1. So if we take radius 1 and simply flip it the other direction, then add it to radius 2, then that will give us our triangle. So we flip radius 1 and add it to radius 2. And then the difference between the two is going to be just completing the triangle on that one. Now for the velocity we're going to do the same thing. We're going to take velocity 2 minus velocity 1. So we take velocity 2 and then we take velocity 1 and then we have to flip it and then add it to velocity 2 and then make another triangle out of that. Now these two triangles, I want to look at these two triangles and see the relationship between the two. Now if you notice, these two triangles both have the same side. So velocity 1 here, that's the magnitude of that side, and velocity 2 is the magnitude of this side. The magnitudes are going to be the same. That's what we said before, that the speed is the same even though the direction is different. So these two triangles, if you believe that the inside angles are going to be the same because velocity 1 was always perpendicular to radius 1 and velocity 2 is perpendicular to radius 2, so the triangles themselves are going to be going to have the same interior angles, and that makes these two triangles similar triangles. So we're going to take these two isosceles triangles and we're going to compare the two. And since they're similar, that means if we take a ratio between the sides, we're going to get the same ratio on both of them. So we take the ratio of delta r over either of these sides. It doesn't matter because they're the same length, so we just call it r. And then delta v over either of these two sides, which is just going to be v. That's going to have the same ratio. Now, if we divide both sides by time, if you notice velocity or the change in radius over time, that's a definition of velocity because that's a difference in distance divided by time. So the radius is the distance, and change in radius over time, that's going to give us a velocity. Now the change in velocity over time, that is the definition of acceleration. That's actually what we're looking for. So if we rearrange this equation, the delta r over t is going to be equal to velocity. So this delta r over t, that becomes velocity, and the r is still on the bottom here. And then the delta v over t becomes the centripetal acceleration, and we still have the v on the bottom here. We take the v over to the top over here, we leave centripetal acceleration by itself, and we get this equation right here. From these two triangles, we can develop the equation for centripetal acceleration. All right, so let's use this equation with an example problem. Your teacher is holding a tennis ball, rolling it in a circle. His arm is 0.7 meters from the center of rotation, and the ball is moving at a speed of 3.8 meters per second. What's the centripetal acceleration? Well, centripetal acceleration is going to be equal to velocity squared over radius. We got the velocity, it's 3.8, and we got the radius, it's 0.7 from the center of the circle. Go ahead and plug those in. 3.8 squared divided by 0.7, that gives us 20.6 meters per second squared. A race car moving around a circular track with a radius of 3,500 meters completes one time around in 135 seconds. So what is the centripetal acceleration here? Now we have the radius is given, but not the velocity. But something to note here is the definition of a period is the amount of time it takes to complete one cycle. Now think about a circle. A circle, for the period, the amount of time it takes to complete one cycle, what do you think the distance is to complete one cycle? The distance around a circle for one cycle is going to be 2 pi r. It's going to be the circumference of the circle. So the velocity is going to be the circumference divided by the period, because the circumference is one time around, and the period is the amount of time to go around once. So the circumference is the distance around one time, and the period is the amount of time for one time, and then we go ahead and divide those, and we figure out that the velocity is 2 pi times the radius divided by the period, and we figured out the velocity is 162.9 meters per second. So we can go ahead and plug that into our centripetal acceleration equation. We get velocity squared over the radius, 162.9 squared divided by 3,500, and we get 7.58 meters per second squared. So what's the force that's actually causing the centripetal motion? Because the thing is, in order for there to be a centripetal force, or in order for there to be a centripetal motion, some acceleration is going to be applied, so some force has to be there. And you can't just say centripetal force because that's not an actual force. There's nothing we can point to and say it's a centripetal force every single time. But we can have a force that supplies that centripetal force. So for a car going around a curve, what keeps the car on the curve as it's going around? Another way of thinking about it is what if this force wasn't there? What would happen? Well, it would slide off to the side. So actually friction is the force that's keeping it in a circular motion. So friction is the force supplying the centripetal motion.
All right, so centripetal force. What is centripetal force? Centripetal force is actually not a force. It is not a force. It is actually a net force. A centripetal force is caused by some other force. For example, if you're in a car and going around a curve, it's not actually a centripetal force that's keeping you in the curve. It's the friction between your tires and the ground. Because if you didn't have that friction, you would slide off and go straight, as opposed to making the curve. So centripetal force, if you ever ask what is the force that's acting to keeping something in a circle, the physical force is never going to be centripetal. But if that force is producing a circular motion, then we call that net force a centripetal force. All right. So again, if there is a net force being applied that is producing a circular motion, we call the net force, we give it a new name, we call it a centripetal force. So that means that if all the forces were added together, the resultant, the net force, produces circular motion. That's our centripetal force. So our centripetal force, since it's the net force, is going to be equal to mass times acceleration. But we already have an equation for centripetal acceleration. So our centripetal force is going to be equal to mass times centripetal acceleration. All right, so some of the problems we're going to be dealing with on this, we got number one, a runner moves at a speed of 8.8 meters per second around a bend. Number two, we got a 580 kilogram car on a flat track, and then we got an airplane on the third example. So let's go ahead and do these.
So now we're going to look at a few examples of some centripetal motion. Number 12, it says a runner moving at a speed of 8.8 meters per second rounds a bend with a radius of 25 meters. What's the centripetal acceleration of the runner, and what agent exerts the force on the runner? So what is actually supplying that force? And again, we can't say centripetal force because centripetal force is a net force. It's not an actual force. Something has to supply that net force that's being applied to the runner. So first we have to figure out his centripetal acceleration. So we got a centripetal acceleration equation, but we got two equations. We got velocity squared over radius, and we also have 4 pi squared radius divided by the period squared. But if you notice, we have the velocity here, and we also have the radius here. So we have the information that we need to use velocity, or the centripetal acceleration equals velocity squared over the radius. So we'll go ahead and plug that in. We figure out that his centripetal acceleration is 3.10 meters per second squared. Now, what's the force that's keeping this runner going around the curve? Well, it's going to be friction, because if he didn't have friction, he would slide off the side. Next one is number 13, says a car racing on a flat track travels at 22 meters per second around a curve with a 56 meter radius. Okay, so the reason it says a flat track is because now friction is going to be the only thing that's going to be able to keep that object in a curve. Normal force is not going to be able to do anything in order to help him. It says find the car's centripetal acceleration, and then what minimum coefficient of static friction between the tires and the road is necessary for the car to round the curve without slipping. Now, if you remember when we talked about how cars are actually driving, cars don't use kinetic friction. They don't use sliding friction in order to move. They use static friction. They use non-sliding friction because you don't want your wheels to slide as you're rounding a curve or as you're driving your car. So first thing, we need to find the centripetal acceleration. Again, we have the velocity and we have the radius. So let's go ahead and use this. It's going to be velocity squared over the radius, and that gives us 8.64 meters per second squared. Now, what minimum coefficient of static friction is needed for the tires necessary to round the curve? Well, in order to figure out coefficient of static friction, we only have one equation. That's force of friction is less than or equal to coefficient of static friction times normal force. So we need to figure out the normal force, and we need to figure out the force of friction. Well, if we draw a free body diagram, then we have a force of gravity downward, a normal force upward, and then the force of friction is what's keeping us in a circle. So this is kind of the front view of the person as they're going around the curve. You got the force of friction towards the center of the circle. So let's do net force in the x direction. If you notice, the net force in the x direction, force of friction is the only force in the x direction. So we use that. Force of friction equals mass times centripetal acceleration, because the acceleration is also in the x direction. So we plug for the net force in the y direction, we have the normal force upward, and we have the force of gravity downward. Go ahead and plug those in. Normal force upward minus force of gravity downward is going to be equal to 0. Now, the reason we couldn't really do anything else over here with the force of friction was because we don't have the mass. The mass is not given to us. So we're going to move on to find normal force. Now, normal force minus force of gravity, that's minus mass times the acceleration due to gravity. Take that to the other side. We figure out that normal force equals mass times the acceleration due to gravity. So we're going to take this equation for force of friction. We're going to take this equation for normal force. We're going to go ahead and plug it into this equation up here. Now, something interesting about this is you notice that there's mass on this side and there's mass on this side. Those two masses are going to cancel. So we don't need to know what the mass is going to be equal to. But in order to find the coefficient of static friction, we have to get that by itself. So we need to divide both sides by gravity. And we get that the coefficient of static friction is greater than or equal to the centripetal acceleration divided by the acceleration due to gravity. So we take the centripetal acceleration, which is 8.64 divided by 9.8, and we get that the coefficient of static friction has to be greater than or equal to 0.882. If it's less than that, then the car is going to slide on the road.